Early commercial data processing was defined by mechanical violence. Heavy, nickel-plated tape had to be jerked into motion, dragged across read heads, and slammed to a halt thousands of times a day. Machines like the ENIAC were engineered for the military to solve complex ballistic calculus. But the dawn of the 1950s brought a different set of demands from the U.S. Census Bureau. A census, or a corporate payroll run, requires simple arithmetic, counting and adding, performed on an unprecedented volume of individual records. In this environment, the system's throughput became the critical metric. Success was no longer dictated by processor speed, but by how fast data could move between mechanical storage and electronic circuits. Engineering a solution to this physical data bottleneck would determine who dominated the first era of commercial computing. The first major contender was the UNIVAC I, a machine optimized specifically for high-volume data handling. Its primary rival, the IBM 702, emerged shortly after to challenge for the same corporate customers. The conflict between these machines centered on a specific engineering choice: the value of high-speed I/O buffering versus the necessity of physical memory stability. Processor clock speeds from this period offer a deceptive view of performance. In commercial workloads, internal speed mattered less than the ability to keep the processor fed with data. IBM would eventually capture the market, but their early architecture actually processed commercial payloads at roughly half the speed of the UNIVAC. Understanding how IBM overcame this architectural deficit requires a close look at the instruction sets and hardware that gave UNIVAC its early edge. Technical specifications from the era show that the UNIVAC I utilized a 72-bit word, designed specifically to minimize wasted processing time. By splitting this 72-bit word into two 36-bit instructions, the system retrieved two distinct commands in a single fetch cycle, each instruction divided into 12 bits for the function code, the command itself, and 18 bits for the data's memory address. These codes, seen here in octal and binary, allowed programmers to trigger operations like add or multiply with minimal electronic overhead. Even with an efficient instruction set, the fast electronic processor still faced a physical reality. It could calculate far faster than a mechanical tape drive could deliver the next record. To prevent the computer from sitting idle, UNIVAC needed a way to decouple the processor from the physical movement of the tape. The solution was a pair of dedicated 60-word registers, the input and output buffers, which acted as high-speed holding areas for data. This architecture allowed simultaneous input, output, and compute. The CPU crunched numbers in main registers, while buffers loaded the next data batch from tape in the background. In repetitive tasks like census waiting, this overlap eliminated gaps where the processor would otherwise wait. Efficiency was further improved by the read backward instruction, which allowed the system to ingest data while the tape spun in reverse. This removed the need to wait for a physical rewind cycle between every batch of records, saving hours over a massive processing run. By decoupling the processor from the tape drive, these asynchronous buffers allowed the UNIVAC to maintain a continuous data flow that no competitor could match. The IBM 702, meanwhile, lacked any equivalent to these simultaneous buffers. IBM's architecture was strictly sequential. The machine had to stop computing to read data, finish the computation, and then stop again to write the result out, leaving the CPU idle and waiting for the tape. For commercial workloads, this sequential design meant the IBM machine took twice as long as the UNIVAC to complete the same task. Despite this speed deficit, the market's preference began to shift toward IBM. UNIVAC's throughput advantage was undermined by its primary memory system, acoustic mercury delay lines. This memory relied on pulses traveling through tubes of liquid mercury. It was volatile and temperamental, requiring precise temperature control and constant maintenance to function. IBM instead adopted magnetic core memory, seen here as an intricate grid of stable wires. This system had no moving parts or liquid elements, making it far more reliable for business operations. Businesses decided that the physical reliability of core memory was more critical to a payroll deadline than the architectural throughput of UNIVAC's buffers. IBM consolidated this lead by establishing a hardware ecosystem that corporate customers were already familiar with. UNIVAC's proprietary tape was made of nickel-plated bronze. While it was fast and dense, it was also highly abrasive to the machines that read it. IBM pushed for a different standard: plastic film tapes. This format was easier to manufacture and integrated better with the punch card environments IBM already controlled. Although the UNIVAC tape offered higher performance, the company was eventually forced to build drives compatible with IBM's media standard to remain competitive. In this instance, UNIVAC's specialized hardware could not overcome the inertia of the emerging IBM standard. By the late 1950s, the competition for hardware dominance had left the industry deeply fragmented. Companies owned machines from UNIVAC, IBM, and DEC that all spoke different binary languages, making it impossible to share software between them. Dr. Grace Hopper, working at the UNIVAC division of Sperry Rand, sought to bridge this gap. Her work led to the creation of A0, the first compiler, and B0, an English language compiler that would become the precursor to COBOL. A compiler takes a single English command, like multiply, and automatically translates it into the distinct machine code required by different brands of hardware. This abstraction meant a company's software no longer had to be rebuilt every time they bought a new computer from a different manufacturer. The 1950s were defined by a struggle for hardware dominance, but Hopper's work signaled a shift where the value of a system no longer lived solely in its iron, but in the software that could outlast it.